Good afternoon. Welcome. Imagine you're a data scientist working for a bank trying to predict who will default on a loan. You gather every variable you can possibly find: income, credit score, number of credit cards, an individual's spending habits, their home ownership status, age, zip code, social media activity, hundreds of features, maybe thousands of features. You train a model and it performs perfectly on the training data. You present it proudly to your team and the resulting stakeholders. But then the model goes live and it fails miserably. Why? This is because the model memorized the data instead of learning the true patterns. It relied heavily on weird accidental relationships, like a certain zip code appearing with only one default, a random spending category correlating with repayment, small noise in the dataset. The model became too confident in too many variables. So what do? Instead of letting the model use every feature freely, you introduce a penalty for complexity. Pretend you tell the model, if you want to use a lot of variables or give them huge weights, you're going to pay a price. Suddenly the model becomes simpler, more stable, and better at predicting new data. Some variables shrink towards zero, and some disappear entirely. The model now focuses on what actually matters. That idea, controlling complexity by penalizing large weights, is exactly what we call regularization. Today we're going to look at two of the most common ways to do this. L1 regularization, otherwise known as Lasso, which can eliminate features completely. L2 regularization, otherwise known as Ridge, which can shrink features smoothly. Regularization is a method used in machine learning to prevent a model from becoming too complex and overfitting the training data. When models become overly complex, they start memorizing the training data set, rather than learning patterns that generalize to new data. Regularization solves this by introducing a penalty for large model coefficients, encouraging the model to remain simpler while still fitting the data well. Overfitting occurs when a machine learning model learns the training data too well. Instead of learning the general relationships in the data, the model begins to learn noise and random fluctuations. This usually happens when a model becomes too complex. For example, when it has too many parameters or features. Regularization helps control this complexity so the model focuses on the most important relationships. Regularization works by modifying the model's loss function. Normally, machine learning models try to minimize prediction error. With regularization, we add an additional penalty term to the loss function that penalizes large coefficients. The lambda function or parameter controls how strong that penalty is. If lambda is small, the model behaves normally. If lambda is larger, the model is forced. L1 regularization, also known as Lasso Regularization, penalizes the absolute values of model coefficients. One important property of L1 regularization is that it can drive some coefficients exactly to zero. This means that the model automatically removes unimportant features from the model. Because of this, L1 regularization is often used when we want both prediction accuracy and feature selection. L2 regularization, also known as ridge regression, penalizes the squared values of the coefficients. Unlike L1 regularization, ridge regression typically does not reduce coefficients exactly to zero. Instead, it shrinks all coefficients closer to zero while keeping every feature in the model. This makes ridge regression useful when features are correlated or when we want to stabilize a model rather than remove features. To summarize, regularization is an important technique in machine learning that helps control model complexity and reduce overfitting. L1 regularization, or lasso regression, penalizes the absolute value of coefficients and can drive some coefficients to zero, which makes it useful for feature selection. L2 regularization, or ridge regression, penalizes the squared magnitude of coefficients and shrinks them towards zero, while keeping all features in the model. In practice, these techniques help create models that perform better on unseen data, which is the ultimate goal of machine learning. As a part 2 of this video, I'll be making a video soon with an example where I demonstrate how we are able to visually see how ridge shrinks coefficients while Lasso can remove features entirely. Thank you for joining me on today's video.